Hello and welcome back to Counting Rocks, an Introduction to Combinatorics at CSU. Today we're going to be talking about solving recursions with generating functions. So last video we talked about finding closed form for generating functions and manipulating them, using generating functions to find other generating functions, and now we're going to actually use our closed formulas to give explicit formulas for sequences that maybe we're counting with or that are given by some recursion. So let's first look at the example of a linear recurrence that we've been looking at in a bunch of videos, where a0 equals 2, a1 equals 5, and an equals 5, an minus 1, minus 6, and minus 2. This is all the math that was done in the previous video, where we solved for the generating function of this recursively defined sequence, and we found the closed formula 2 minus 5x over 1 minus 5x plus 6x squared. Now let's use that closed formula to write the generating function in a different way to extract the coefficients to get an explicit formula. So what we can do when we have a quadratic on the bottom is factor it using the roots of sort of the opposite polynomial. So notice that 1 minus 5x plus 6x squared factors as 1 minus 3x times 1 minus 2x. This is sort of the opposite of factoring the characteristic polynomial, which is actually x squared minus 5x plus 6, meaning you flip around the coefficients of which one's on the constant term, which one's on the x squared. If you take that polynomial, it would factor as x minus 3 times x minus 2, and we've flipped these two as well. So we're looking at almost like the characteristic polynomial, but backwards, and we're finding the same roots, 3 and 2, coming up again. But once we've factored the denominator, we can use a method called partial fractions from algebra to write this fraction as some number over 1 minus 3x plus some number over 1 minus 2x. This will enable us to use the geometric series formula to re-expand these two terms in a different way. So first let's solve for a and b. If we added these fractions and we do a times 1 minus 2x plus b times 1 minus 3x on the top divided by the product, then what we get on the top should match 2 minus 5x. So we should get that a plus b is 2, and 2a plus 3b is 5, so that we match the coefficients of x and of 1. And so that gives us two equations in two variables, a plus b equals 2, 2a plus 3b equals 5, and if you solve this, you notice a equals b equals 1 satisfies these two equations. So that means that in this problem, we actually just have 1 over 1 minus 3x plus 1 over 1 minus 2x is another way to write the generating function. And once we have it like that, then by binomial substitution, this is the geometric series formula with 3x plugged in. So we get the generating function for 3 to the n. And the other one is the generating function for 2 to the n. So we add those together by the rule for adding generating functions, and we get 3 to the n plus 2 to the n as the coefficient of x to the n. But a of x is also, remember, the generating function for the sequence a sub n. Now, two generating functions are equal if and only if their coefficients are equal. So that means 3 to the n plus 2 to the n has to equal a sub n for all n. This means that we've found an explicit formula. A sub n equals 3 to the n plus 2 to the n for all n. We started with a recursive formula, we found a closed formula for the generating function, then we calculated that generating function in a different way, and we got an explicit formula. So this is almost like counting in two ways, except we're really doing algebra in two ways. Write the generating function in two different ways, get two different coefficient sequences, and those sequences must be equal. Now let's look at the case of when we have repeated roots in a linear recurrence, and we're going to see how the same patterns that we had for linear recurrences in the recurrences video are coming up here. So now say we have this recursion, a0 equals 3, a1 equals 8, and a sub n equals 4 a sub n minus 1 minus 4 a sub n minus 2. We can solve for a of x in the same way as we did for the previous one, where we take the a of x generating function and we subtract 4x a of x and add back 4x squared a of x, and these terms will all cancel because we'll get things like a2 minus 4a1 plus 4a0. That has to be 0. Same thing for all these columns. And you're just left with these first two columns, which simplify to 3 minus 4x when you plug in the initial conditions that are given. That means that 1 minus 4x plus 4x squared times a of x equals 3 minus 4x. We solve for a of x, and we have a closed form for the generating function a of x. The problem is, in this case, the denominator factors as 1 minus 2x quantity squared. That needs a different partial fractions approach than the other one. So when you have repeated roots, we can't just write this as something over 1 minus 2x plus something else over 1 minus 2x. In this case, what we do is write it as a over 1 minus 2x plus b over 1 minus 2x quantity squared. And we do actually have a way of dealing with this because we saw that 1 over 1 minus x quantity squared is the generating function of the counting sequence in the previous video. So we can use that sequence and use monomial substitution to get the answer. So let's see what these numbers have to be. If we sort of multiply the top and bottom of this one by 1 minus 2x and add the fractions together, we get a minus 2ax plus b. So a plus b has to match the 3, and minus 2a has to match the 4. And when you solve, that means that a equals 2 and b equals 1. Plugging that back in, we know that a of x is 2 over 1 minus 2x plus 1 over 1 minus 2x quantity squared. So this one is just 2 times the monomial substitution of 2x into the geometric series, so we get 2 times 2 to the n as the coefficient of x to the n for this generating function. And for this term, we have that if this was 2x was just x, it would be the sum of n plus 1 times x to the n, and we just have a 2 to the n in there because we monomial substitute 2x in for x. And so now we can add these together, and we find that a sub n, the coefficient of x to the n, is 2 times 2 to the n plus n plus 1 times 2 to the n, and when we factor out the 2 to the n, we get n plus 3 times 2 to the n. So we found, again, an explicit formula for a sub n by using generating functions, writing them in a different way, and expanding using series that we already know. Now let's look back at the Towers of Hanoi problem. So we had this recursion where the Tower of Hanoi with n pigs takes h sub n steps where h sub 0 is 0, and h sub n is 2h sub n minus 1 plus 1 for all larger n. Now, if we write out the generating function h of x for the Towers of Hanoi sequence, and we multiply it by 2x, then we'll get the shifted sequence 2h sub n minus 1 and the generating function for that. And so if you subtract these, we should get 1, right? So h sub 0 is 0, but then after that, we're subtracting h sub 1 minus 2h0, we know that's 1, h sub 2 minus 2h1, we know that's 1, all by the recursion. So we're going to get 0 plus x squared plus x cubed plus dot dot dot. What did we do? We subtracted h of x minus 2x h of x, so we get 1 minus 2x h of x. And so we have this equation, 1 minus 2x h of x is x times the geometric series, which is x over 1 minus x. And so we found a closed formula for h of x by dividing both sides of this by 1 minus 2x. Now, once we've done that, then how can we find an explicit formula for the Towers of Hanoi sequence? Well, h of x is now x over 1 minus x times 1 minus 2x, and so we can write that as a over 1 minus x plus b over 1 minus 2x, and you solve for that again to make this summation be x on the top, and you find a equals minus 1 and b equals 1. And so now let's re-expand with the geometric series. We get 1 over 1 minus 2x minus 1 over 1 minus x from our solving and plugging back in. This one gives the generating function for 2 to the n, and this is the geometric series. So when we subtract these, we just get 2 to the n minus 1 as the nth coefficient. Again, this matches h sub n, and so h sub n equals 2 to the n minus 1. Now, we found that when we did Towers of Hanoi by guess and check. We wrote out a bunch of Towers of Hanoi sequences, we noticed that it looked like 1 less than a 2 power, and then we checked that satisfied the recursion. But if it's not easy to guess what that answer is, there would have been no way of getting a handle on the explicit formula unless we did this partial fractions computation and used generating functions. So that's the power of generating functions, is solving for sequences in a way that you couldn't do without the power of generating functions and some algebra that we have built up as well. So now you try. Use generating functions to find an explicit formula for the sequence defined by a0 equals 0, a1 equals 0, and for all n greater than or equal to 2, a sub n equals 5a sub n minus 1 minus 6a sub n minus 2 plus 1. So this plus 1, first of all, gets us off the ground, 0, 0, 1, and then the recursion will sort of start up after that. And also notice it's almost like our recursion that we had before, except we have a plus 1. So it's nonlinear. We can't use our linear recurrence formula, but we can combine it with sort of the Towers of Hanoi strategy to solve and find an explicit formula for this anyway. So that's all for today, and I'll see you next time.